Okay, good morning, everyone. Welcome to the second week of the. I guess there are some new participants this week. So I'll just mention a few things regarding the program logistics. So please wear these badges at all times. This is necessary for you to get lunch and other food and so on. And when you leave, actually, you can leave these badges at the desk because we recycle them. So the lunch is at the first floor of the cafeteria, which you all must have seen. And coffee will be, there are coffee breaks and you get coffee outside. There's a 24-hour healthcare center and there's a gym and swimming pool and so on, which you are free to use. There are cycles at the main gate, which you can take and you can use it to explore the neighborhood. But I should warn you that there are, as I told you last week, there are two leopards which are around. So it's a bit, so especially in the dark and very early morning, please be careful. I mean, in fact, I saw a video where you can see the two leopards in some house. So to be careful. For any problems, you can send an email to Raju at the email QU2TR email, or to me and Raphael, who's the other organizer. The other thing is, please send the slides of your talks so that we can upload them on the website as soon as possible. This helps people to follow the lectures. And all the talks are there on YouTube. I mean, so this is, we still don't put them on the website since they need some formatting, but we'll send a link to all participants and they can actually see the YouTube videos recordings at all times. Okay, so we'll start the session. The chair of the session is Raphael. And
thanks, Abhishek. Thanks, Klaus, to give this lecture.
Good, thank you very much.
We are very happy that you come.
So before I start giving my talk, I'd like to thank the organizers for running this whole fantastic, amazing program, and also for inviting me to come and have the pleasure of meeting colleagues here and discussing a topic that I just love in physics. It's been with me for the last 30 years. I decided to structure my 3 lectures. So I have 3 times 1.5 hours. You'll be well tired of listening to me. I can promise you that already now. I will structure my lecture, so I'll give the first lecture colloquium style. So that will be a kind of physics colloquium where I'll try to put quantum trajectories into context of quantum mechanics, some of the fundamental questions in quantum mechanics, some of the applications. Why do we need a theory of observed quantum systems? What are the quantum systems you would like to go and observe and use these methods? And then in my 2 next lectures, I will then dive in a little bit more school-like. I don't think the sound is very good. Do you also hear kind of hissing echo? Okay, is that something we can, is the microphone amplified a little too much? Okay, yeah, now it sounds better in my ears at least. Okay, so in my 2 next lectures, Tuesday and Thursday, I will dive into quantum trajectories, which is also the topic of the lecture today, but talking more in detail, more examples. What do we know about a monitored quantum system? What is the dynamics of a quantum system that we are monitoring? What is it doing? And that is, of course, very interesting also in these days with quantum technologies where we want to steer quantum systems to have certain functions for us. And my lecture on Thursday, I call it almost the same, but it's what can we learn with a monitored quantum system. So that lecture will be based on discussions of quantum sensing, using a quantum system as a sensor, sensing some influence, for example, a magnetic field or electric field or acceleration or some effect that makes the system evolve. And if you're probing it continuously, then you're having a probe of that kind of dynamics. And it turns out that the quantum trajectory theory is also the ideal theory of sensing, because it's a tool that tells you what is actually the value that you're trying to measure with this little quantum gap. So that will be my lecture on Thursday. So let's dive into this colloquium style lecture. And maybe it's because of my age, but I like to go back, if not to Newton every time, then at least back to the beginning of quantum mechanics. And you know, quantum mechanics or quantum physics started with Planck 1900, where he came up with the quantization of light. Actually, what he really quantized was the exchange of energy between the radiation field and matter. So he concluded not that there were particles of light or photons, as we call them today, but when you are in thermal equilibrium with the walls, for example, of a chamber, the energy exchange with the walls comes in forms of quanta. And Einstein bluntly, a few years later, said that's because the radiation field contains these quanta. And that's the thing, the particles that we call photons today. These are, of course, as you know, quantized. The energy of one of these quanta or photons is Planck's constant times the frequency of light. Few years, well, Einstein already had, that's very interesting, if you read his 1905 article, that he has some struggle because the light is, of course, the electromagnetic field. So you have a Maxwell theory of light. So you have Maxwell's equation, electric and magnetic fields. And now you claim that maybe in this particular solution, there's only one quantum. So if you have an array of detectors, then you will see the photon or detect the radiation by only one of the detectors. And Einstein asked himself in this article, what happens to the electric and magnetic field in the rest of space when I have the click on that particular detector? It's exactly the same question that, of course, bothers Einstein when we have the quantum mechanical wave function and you see the electron in a particular point in space. That is already in his 1905, his own article about the quantization of light. It's also the same question, of course, as we later face in quantum mechanics. The quantum mechanics, or rather the quantization of matter, began with Niels Bohr, who in 1913 made his model of the atom. You couldn't make it much earlier because the atomic nucleus was discovered by Rutherford in 1911. And Bohr was what we would today call an interdisciplinary scientist. So while Rutherford and Thomson and these people were the particle physicists of their time, discovering the electron, discovering the nucleus, these guys had no interest in chemistry and they had no interest in spectroscopy. There was also a spectroscopy and chemistry community. They were doing beautiful physics, but they were not interested in the particle physics. And Bohr is, of course, linking those two because he's using this model composed of the particles to explain the spectroscopy of the atoms. So he says that this mechanical model that we all learn about in school of orbits of the electrons around the nucleus and Bohr's quantization of these orbits, there are only certain orbits, that's what explains that the electron, when it jumps, can only emit frequencies of the values that are allowed here by energy conservation. So it's actually an early case of bringing two silos together in physics, and it could not happen much earlier because you needed the ingredients on both sides. So this Bohr postulate explained that all atoms emit and absorb light quanta at only definite frequencies, and he actually had a quantitative theory based on some really clever insightful thinking, the correspondence principle, that gave an analytical formula for these energy levels that matched for hydrogen with 5-digit precision. And if you correct for special relativity, actually 7-digit precision, which is the best astonishing agreement between any theory and any experiment at that time. The equation is 15% off for helium. And that was, of course, struggling Bohr and Sommerfeld and many others for the next 10 years. You also know that this theory is not right. It's actually wrong. The true theory is quantum mechanics that came in the 1920s. And I cut this story a little bit short because it's not a review talk on quantum physics, but the Schrödinger equation is the Schrödinger equation. You have to solve for this wave function psi. These are pictures of the solutions of the Schrödinger equation for hydrogen. And the picture here, some of you may have seen some of my talks before, and I always say that John Travolta has nothing to do with quantum mechanics, but actually Olivia Newton-John has, because her grandfather was Max Born. And Max Born told us that not only do we have frequencies of these wave patterns which match the Bohr frequencies and the energies of the light we see, but the spatial distribution shown here reflect the probability for where you find the particle if you do experiments on looking for particles. So that is quantum mechanics, and the textbooks are summarizing all these into the tools. We have to solve the Schrödinger equation to find the wave function, later generalized to density matrices. There are physical quantities. They're all represented by observables, operators who have eigenvalues, and the probability when you do a measurement for getting any of these eigenvalues, that's the only allowed results of a measurement, are given from the wave function. There are also mean values you can predict by that formula, but that actually only means that you will get the different eigenvalues with probabilities. So that's going to be the weighted average of these A's. And that's what we refer to as the expectation value or mean value. And there's also the projection postulate that if you do a measurement, your wave function will collapse onto the corresponding eigenstate. That's in almost any first-year quantum mechanics textbook. Some have a little bit of history and some go directly onto this formula. And that's, of course, what we do. The meaning of the wave function, just to dwell a little bit upon that, because we are going to talk a lot about measurements in these quantum trajectory talks. So therefore, it's nice to know what is it actually that happens when you have a quantum description and you do a measurement. So the story I told you is that you have a wave function, and the wave function here, just a simple formula I'm just showing you here, that is going to give us the probability distribution for where you find the particle if you do a measurement of the position of the particle. And if you see just one particle, you see it somewhere. And if you see many particles, you can make a histogram. And that is an indication of how that histogram forms if you detect many particles. And it then gets the shape of this wave function square. Now, Einstein, of course, asked himself, what if I do only one experiment? What is it that governs the precise outcome of a single experiment? So here, I saw it at that particular point. And Einstein would like to, maybe that to not be completely randomly decided, but maybe there could be, maybe the particle was already there, and we just didn't know. Okay, that's how probabilities often work. Or maybe the particle was just wandering around, but spending its time in proportion to the wave function in different locations in space. So that no matter when you look, the statistical agreement with the probability distribution here would also be in place. There could be many underlying reasons for the randomness and for the actual outcome of the experiments. And if there was such an underlying reason, it would be what we would maybe call a hidden variable, because there would be a hidden truth underneath this physics. And I just have to say that Schrödinger, of course, being the father of the wave function, had tried in the beginning to make the picture that the particle had become a wave. And I actually think that's the message that many students go away with from our lectures in quantum mechanics, that in the microscopic world, particles are waves. They are wave functions, and that's what they are. But of course, that's not the whole solution, because if you had only the wave function, that would not explain why when you see the particle, you see it in these locations as if it is a classical particle. So a wave interpretation of quantum mechanics doesn't explain the outcome of measurements. And Schrödinger's idea was that, okay, of course I realize there are random measurements. It could be that because of interaction with the measurement apparatus, this wave function changes form and in some sense just concentrates a little bit more. Now, Schrödinger abandoned this idea himself because you run into issues with entanglement and these things. But as an initial idea, this dynamical picture of a wave function who collapses, of course, still exists in some interpretations of quantum mechanics today. All of that was very troubling also to the scientists, so you may not all have seen some of these quotes, but Einstein was very unhappy with the situation, and he has a quote here: if quantum theory is correct, it signifies the end of physics as a science. Schrödinger was equally unhappy. I do not like it, and I'm sorry I ever had anything to do with it. So that's, of course, a drastic statement from after he got the Nobel Prize for the quantum mechanics, to say that he didn't like what he had done. And Bauer said, those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. And I think these are interesting but also well-motivated statements for the situation of quantum mechanics at the time. Now, along with the discussion of what the theory means, of course, it was also applied to all of physics. So it was sort of co-discovered with the physical phenomena. So the atom was discovered at the same time as the quantum mechanics who describes the atoms. And in the next years, the nuclear physics was discovered. The new particles inside the nuclei was discovered together with the Schrödinger equation that governs the motion of the nucleons. And particle physics, of course, is an adaptation of quantum mechanics. Lots of modifications, relativity, fields, and whatnot, but it's still the same basic idea. It's a quantum theory that describes all the microscopic phenomena. In the opposite direction, of course, molecules, which were already in Bohr's early papers, and solids and surfaces are all the disciplines in atomic physics or solid-state physics, particle physics, which are governed by quantum mechanics. And when people are doing theory, we're not struggling with the interpretation of quantum mechanics. We shut up and calculate, as sometimes quoted. We calculate mean values, we calculate probabilities, and of course, they are always right, and they match. We calculate spectroscopy, the eigenvalues of the Schrödinger equation. So there's not much philosophy in the interpretation of that, but it's still, for Einstein and Schrödinger, kind of shaky ground, because what is really happening in the microscopic world is not so clear. And they also wanted maybe an understanding of that part. I like a quote from Schrödinger as late as 1952, where he tries to resolve this measurement problem by this statement. He says, it's fair to state that we are not experimenting with single particles any more than we can raise ichthyosauria in the zoo. So ichthyosauria is this kind of dinosaur species which I would definitely find difficult to raise in a zoo. It's extinct for 170 million years. But the idea of the quote here is that we are only describing always large ensembles of particles. It's actually not a probability theory, because we are doing experiments with billions and billions of atoms, so we see distributions all the time, and they are deterministic. And he says it's as crazy to think of single atom physics as doing biology with this extinct species sitting here. And that would solve the measurement problem by claiming that it doesn't exist because it's an abstraction to work on the single particle. And that's of course nice, but it's not true with modern physics, as you know. I'd like to, before we go to these modern bits and pieces and tiny single individual quantum systems, I'd like to point to one maybe surprising area where we were suddenly had to realize that measurements are random and measurements have an effect of the quantum system. And that came from astronomy, so it's a historical experiment in quantum optics. And I would say this is a founding experiment observation for quantum optics. There's not much quantum optics in it, but it made people reflect on of light and detection of light in new ways. So we are back in 1956 in Australia. Here are two parabolic disks looking into space. And the idea is that you find some object, a stellar object in the sky, and then you can look at the signal received by these two parabolas. And if there's a difference in the distance to this object in the sky, then you will see it because the two signals will be replica of each other, but with a small delay. So you can imagine that you have a noisy signal from the star seen by one parabola, and then you have the one seen by the other parabola, and they are displaced in time. And if you move the one, then you can see now they match. So this is not how they do it, but this is how I can illustrate the principle that you can measure the time delay just by seeing when these two figures actually match. And then you can do some trigonometry, and then you can maybe determine the distance to the star or even more advanced things in space. These are intensity measurements. Today they, of course, also do amplitude measurements in space interferometry. Now, this would not work if the intensity from the light from the star would be completely constant. Right? Then there would not be any signal here. If stars were lasers, it would be very difficult to apply this method, actually. But because it's noisy, it is possible. And that made people think a little bit about the noise in detection signals. And it would work if the time scale of this noise would be good enough to actually also resolve the delay. So you have to understand not only that there's a noise, but also what is the temporal correlations in that noise. So a quantifier of that would be how is the intensity at time t correlated with the intensity tau later. Because if that has a clear dependence on tau, then you'll be able to see if there has been a delay by that amount tau. So here's a measurement actually done by these gentlemen, Hembury, Brown, and Twiss, with a light lamp, rubidium lamp, I believe. They show that the intensity, of course, at the same time is maximum, and then if you look at delays, then this is going to fall off the average of this quantity. And that is the kind of quantification of these noise in these signals. And I think it was more or less new to the community that, wow, there's actually information hiding in these correlations, noise correlation, the randomness of the signal, which is important. And people also started thinking over the next few years, what is the quantum nature of light having to do with this thing? So Laurie Glauber was looking into that, and that's on my next slide. There were ideas coming shortly after Glauber's theory, is the pioneer of photodetection, that some of these fluctuations may prove whether this light is of a quantum nature or not. And that's very interesting, just as a historical remark, because while quantum mechanics was, of course, immediately accepted, there's up until the 60s a strong community who believed in neoclassical theories of light. Maybe all optical phenomena could be understood as classical fluctuating complex fields. Okay, there's still a tiny group now of people who believe that that is still true. And you might say, why would you like to do that? But I mean, why use quantum theory if it could be described by classical theory? Therefore, this proving the quantum nature of light has been a thing you see in many, many experiments and theories from the 1970s, actually up until this very day, showing that this light is non-classical. Somebody would give their mother-in-law's left arm to do such an experiment. And then, of course, also a more dynamical theory, quantum theory of the fluctuations in the detector clicks in these devices who measure these records, because this is not only the noise coming from the source, this is also the noise coming from the fact that your detector has a probabilistic element to it. So there's a whole lot of things that took its starting point in something which is actually just more like classical thermal light, but showing correlations that force the community to think about that. And of course, this is crucial, or it's intimately related to what we will later talk about in quantum trajectories, because this is also observing noisy detection records in the lab. So, and I would also like to say that although a lot of this can be connected to interpretations of quantum mechanics and measurement theory and whatnot, all of this was done for an entirely non-philosophical reason. You're just looking at the nature of these signals. I never saw Roy Glauber, who I admire deeply as a fantastic physicist. I never saw him into discussions of the philosophy of quantum mechanics. And you shouldn't do it unless it's necessary or unless you find it wonderfully entertaining to do that. So here's a mini challenge already. So we have a quantum mechanics textbooks, which is what we still teach today. It's just the same things as I showed you before. And here is a detector who detects light. So I have a light beam hitting a detector, and what is happening is I have clicks coming out of the detector. That's the nature of the detector. So photon counting will give you clicks at different times, and in between there are no clicks. So how is that related to the quantum theory in the textbook? What is the state, and what is the observable that we are measuring by these detector clicks? What eigenvalues is being measured here? What mean value is being measured here? What is the state during and after the measurements that are actually being done by this apparatus? And that is not clear from the textbook, and it's also because the textbook is actually not complete. This is a more general kind of measurement than is described in the textbook, and this is what Glauber developed in 1963. He got the Nobel Prize for that work many years later. So I just want to share that with you, because we will see trends of the same kind of thinking in all the quantum trajectory work. Let me also make a personal statement just about myself. I did a master's degree in atomic structure, and I got a PhD grant to study the role of atomic structure in collision physics. And then by accident, I read Roy Glauber's paper from 1963. It was already a 25-year-old paper, so it was not brand new, but it was brand new to me. I had never heard about that. I fell completely in love with that paper, and I kept it in my backpack for the next year. And because, wow, this is fantastic. So, I mean, you know a lot of this physics already, so I cannot amaze you with the physics. But I mean, think about how great it actually is, the way that Glauber is telling this story. At least I was very impressed. So this is the experiment. And Glauber said, well, what is really happening here is, of course, the photoelectric effect. The light hits a material from which you can ionize electrons. Either it could be atoms that get ionized, or it could be a solid state system where you lift electrons from the valence band into the conduction band. Then you have a voltage to accelerate these electrons. Maybe they get amplified in a cascade, and you get a macroscopic current signal. And that's the click on the detector. But the physical process of detection is actually the detection of an electron, right, that has been liberated by the photon. So if you want to describe this, then you have to have a Hamiltonian who describes that interaction. And the central element of that Hamiltonian is that there is an annihilation of the photon and the excitation. And this gamma plus is just an operator who lifts the electrons up into an excited state. Think about it like a racing operator for a harmonic oscillator, or a Pauli racing operator is an operator who lifts the electron into the excited state. So the time evolution is going to be in one short time step. Before you have any click, you're just going to have a state of the field and a state of the detector. All the electrons are in the bound state, the field is coming in, and then the time evolution is going to raise a small component of the wave function. So you're going to have this state, remove a photon, excite the electron with a small probability, because we saw the Schrödinger equation in a small time step dt. So your state after small time step dt is this one. So it has the original component and a small component where a photon has been absorbed and the electron has been excited. And when you want to detect the click, that's the same thing as asking, is there a free electron or not? And the free electron is that component of the total wave function. So this is the state in which there is an electron. And the probability of having that electron is the norm of that part of the wave function, because that's the probability to be in that state. So we are actually not measuring a field observable A. The operator A that we measure in the quantum mechanics textbook is not the field. It's actually the electron population of that excited state, okay? We are detecting a liberated electron in the detector. We are not projecting the state of light on an eigenstate of any field operator. We are projecting the state onto this component that I show you here, right? Because that's the component in which that electron is sitting. And that actually means that for what the field concerns, this is the state where you have removed a photon. That's the state where you have annihilated a photon on the field state. So your field state is manipulated by this operation by having the A operator acting on it. Okay, so that's not a projection operator. That's an active process of removing a photon. And then, so of course, that's cool. That is the dynamics. That's also what's going to be our trajectories later on. We're going to do things to wave functions which are not necessarily projective, but actions that have to do with the measurement outcomes. There's a little remark you can immediately do. You can, of course, say, what's the probability for the click? The probability for the click is the norm of that state, or proportional to the norm of this guy. Of course, dt also matters here. But if you're looking at this component here, the norm is this guy squared. And the square, or the norm of a state, is taking the matrix element of this vector with itself, or the scalar product. So what the field concerns, you should take A acting on the field state, and then you should write the same thing as a bra, and then you should calculate this scalar product. And look at it, you say, oh gosh, that's nice. That's actually the mean value of the operator A dagger A in the field, which is the number operator of the field. So the probability for the click is going to be proportional to the number of photons in the field. So if you measure many, many photons and you extract the intensity of clicks, that's going to be proportional to the mean number of photon number in the field. So the photon counter is actually counting the photon number in the field, but not as an operator who projects on the eigenstate, but as an operator who has a mean value that we can relate to the rate of clicks in the detection record. I think that's pretty beautiful, right? But the most beautiful part and the most important message of this slide is the dynamics involved in this measurement process, that there's actually another system who interacts with the field. So this operator is interesting, but it's not the one we measure directly as such. We do measure the photon number in an average sense, and if you look at correlations, the correlations that Hanbury-Brown and Twist were looking at, then there will also be now a story to be told. Because if I have a click at 2 different times, then in fact I should apply this thing at the earlier time, but then I should apply it again at a later time. So that means you're facing something like removing a photon, creating an electron time t1, and then removing another photon and raising another electron at time t2 on this state. So here you see there's a little bit of a story, because first you remove one photon, and then you're going to look at what's the probability not only for removing one, but later removing another one. And you can immediately see that there can be correlations here, because if I remove one photon, the resulting state has one photon less. And then the probability to see the next photon may be lower because I have removed one photon. That's true if you have a state with a definite number of photons. Quite ironically, there are also states of light where removing a photon makes the photon number higher. Okay? These are the thermal states, for example, because the thermal statistics is a distribution over the different number states. And when you act with the annihilation operator, you also get a factor square root of n. And that means that all the high n states get a factor in front of them. And that factor is giving them higher probabilities. So therefore, the photon number is actually multiplied by 2 when you remove a photon from a thermal state. So that's kind of a funny effect. So that explains why thermal light sources give more noisy signals, because getting one click gives you a higher chance to see the next click, while coherent light, which is an eigenstate of the annihilation operator, gives you completely smooth, non-fluctuating, because you don't change the photon number when you act on a coherent state. And Fock state will give you sub-Poissonian statistics, because removing a photon reduces the probability to get the next photon, or anti-bunching effects. So this little narrative in Glauber's 1963 is actually also a precursor for the quantum trajectories, namely that the measurements have a back action that you can see in the next measurement you do. But he doesn't call it trajectories, and he doesn't develop it into a stochastic theory. He turns it into a deterministic theory, because this guy has mean values. So these correlation functions can be calculated by of course, methods, and we call it often the quantum regression theorem. But Glauber made just a general formula saying everything you do that involves measurements over many times will be this kind of story, that you annihilate photons at times t1, t2, t3, t4, and then you have to take the norm of that state. That's the probability for this event to happen, and that is Glauber's theory. Now let's come to some physical systems apart from light, of course in the quantum optical world, we are looking at atoms. Here they're interacting with microwave fields. These are ions in ion traps. They interact with photonic fields. You can trap neutral atoms in atom traps. And when you have single atoms to work with, then you look at the light coming from these atoms. And that's very exciting. It's exactly Schrödinger's ichthyosaur, or because there is only one particle. And if you have a single trapped ion, it will actually emit photons. And then you can still look at the ion. It survives, of course. It's still there, ready to emit the next photon into your face. And so quantum optics people realized and very much built on first photo detection theory. Then I would admit that later, these systems in themselves, the ions and the atoms, became so interesting topics that the light was not the significant component anymore. And there was at the Max Planck Institute for Quantum Optics in Garching near Munich, Herbert Walter was the director for many years. And I remember once somebody asked him, so what is actually quantum optics? And Herbert Walter, he said, quantum optics is what I do. So I like that. It's also what I do. So we call it quantum optics, even if there's no optics. Actually, he was also doing trapped ions, which were not even in the quantum state. So it was neither quantum nor optics, but it was the control of atomic motion. And of course, it's also in this realm of controlling simple systems, which have a quantum nature to them. Today, we have invited our friends from other communities, or rather they have invited themselves by having superior systems to simple atoms. So you have quantum dot system, electrostatically confined electrons here in interfaces, superconducting qubits, optomechanical devices. These are, of course, also single systems, and they are now being operated in the quantum regime. And when we do measurements on them, if we reflect light on them and we detect the light, for example, then we have the same story as Glauber, that we are doing something on the quantum state, and that goes back and affects these systems. So we have lots of single quantum systems that we can monitor with light, and we have this effective theory describing how that monitoring constantly modifies the state of the system. It's not a single measurement like in Griffith's quantum mechanics. It's measurements we call them continuous measurements. Of course, clicks are not continuous, but we call it still continuous measurements because I'm probing all the time. And then I get the clicks whenever I get the clicks, but in every DT, I do the measurement. Most of the time, the answer is 0, but that's also a measurement. And so continuous measurement means a system you can look at more or less continuously in time. Now, a little bit on the, maybe not philosophy, but then at least a statement about this ichthyosaur issue here. So this is a drawing from an article by Wojciech Cedric discussing the paradox or the issues having a classical world in which we are all living, and then we have this quantum phenomena described by quantum mechanics. This is a kind of ironical drawing that we cannot use our classical concepts in the quantum world. Here we have the atoms described by Schrödinger mechanics. We can affect atoms because we can shine light on them. So I can classically turn on a perturbation on a system. So I can drive the system with something I control in the classical world. And then, of course, we can also do measurements. So there can be photons coming out, and I can detect these photons. And that's a classical detection record done by my classical apparatus, and I'm the classical person hearing the click. And that also affects the dynamics of the quantum system. So this marriage of quantum dynamics with our classical control and our classical experiments is with us now in the lab. So the measurements on the single quantum system imply wave function collapse or back action or state reduction. These are all the same thing, but the way we describe what we do in the formalism on the quantum system. The removal of the photon in the Glauber theory is such an event also to be done here. It's conditions the time evolution, but it's also very interesting, and that's what puzzled and annoyed Einstein. It's non-local because it's something I do out here, which has consequences for the state up there. I'll come back later also both today and tomorrow, in this apparent conflict that you can do something one place in space and something happens another place in space. Niels Bohr realized this, of course, also very early. So in fact, he took a break between 1913 and 1927. Then he came back again, now being the person who liked to interpret quantum mechanics and the famous Bohr and Einstein discussion. This is shortly before the famous Solvay conference in Brussels. He spoke at a Como lecture at Lake Como in Italy, and he talks about the measurement process as being a complete rupture in the causal description of the dynamical behavior of the system, which of course it is because you do something really drastic to the state. It later, of course, led to what we call the Copenhagen interpretation. Now, from a pragmatic point of view, I have a quantum system. This is the green blob. It's described by its own Hamiltonian. It's probably affected upon by some perturbations. It might also be interacting with some heat baths, so there's some rate processes going on. And then there's some part of the system that gives rise to a signal, and that signal I record over time. So here is my signal recorded over time. Such a system would generally be described by a density matrix, and this density matrix is now going to be conditioned on the measurement record. So if I measure and measure and measure, then the state will evolve according to these measurements. The same way as I removed the photon from the field when I detected the photon in Glauber's theory. So if I monitor a quantum system until time t, what does quantum mechanics tell us about the state at time t? And it tells us exactly what is this rho sitting here. But let me jump to an easier version, and that's actually our first paper on what Howard Carmichael called quantum trajectories. I think it's a wonderful name. It's much better. We call this the Monte Carlo wave function method, and that I'll tell you later why we called it that. But I mean, quantum trajectories, and actually the work by Carmichael was much more insightful than our work. But the technique here is nice, and this is a figure from an equation just copied out of our old paper. So I have an atom. That atom has a ground state and an excited state. So it's a very simple system, and it can be prepared in a superposition of these two states. Amplitude A, amplitude B, and then there's going to be a time phase factor, of course, because this is an excited state. Now, this is not the whole world. The whole world, the wave function of everything, would also include the quantized field. So this initial state, will not only be the atomic state. I have added these 0 kets here, which signify that there's no photon. There's only the atom. But the reason that that is a state is, of course, that the light field is also quantized. And this is just one state of the quantized field, this vacuum state. What can happen is that this excited atom can go to the ground state and emit a photon. Okay? So now I really need the quantum states of the light field. So after a little time dt, I may have some amplitude populating the ground state of the atom and one photon in mode lambda, for example, in direction in space, or with a wave vector, which is labeled by this lambda sitting here. I'm not going to solve this equation. This was done by Bichner and Weisskopf back in 1930-31, but I'm just going to make this little drawing illustrating that your state is now a superposition of a component with no photon in it and a component which is ground state with one photon in it. And what we do when we do density matrices, so if I don't actually see this photon, then if I know that state, I can tell you everything about the atom. I can tell what's the ground state population. That's the sum of that population and that population. I can tell you what's the excited state population. That's the sum of that population and that population. I can also tell you what's the dipole moment. That's associated with the coherence between those two states plus the coherence between those two states. There's no coherence here because there's no population. So I actually know any mean value of the atomic system, and the density matrix is actually the one who can keep track of all these mean values. And to a good approximation, we can get a closed equation for those mean values. We can get a closed equation for the density matrix, which is called the master equation. So it's really the reduced state. We call it the reduced density matrix because I'm tracing out the field degrees of freedom. That means I have to incoherently add what I get from 0 photon and from 1 photon. So that's a standard programming in driving master equations, and this leads to a density matrix for which we can actually get a dynamical equation too. And here's just shown how the two components are being added, of course, from the state. But there's another solution. That is, of course, to say you have a good photon detector. And when in this paper, we actually didn't want to make a theory for detection of photons. We wanted to make a theory to reproduce the master equation results. But we said we can reproduce those by statistically taking either that part or that part, because they are added incoherently. So it is as if the system is either here or here, but with those weight factors. And instead of adding them with weight factors, we can simulate and take one some of the time and the other one some of the time. And that will give the same average. But it's physically motivated. It's not only a mathematical trick, because picking this component or picking that component is what you would do by the projection postulate if you count the number of photons. Because this left part is the component with 0 photon, and this right part is the one with 1 photon in it. Right? So this is like Glauber's argument that we do learn something. We learn in this case something about atoms by measuring the field. He learned something by the field by measuring the excited electrons, but it's the same story. So we said, let's simulate the experiment where I count the photons. I get no click. Well, then I project on the no click part, the 0 photon part, which is that superposition state. or I get a click, and then I project on the one photon part, and that means that state. So that's the evolution of the quantum system. And just like Glauber, you can see that the two possible states you get, even though you have done a measurement, these are not two orthogonal states. This is a ground state, and this is a superposition involving the ground state. And the reason is, of course, I did not do a measurement on the atom. I did the measurement on the field, and therefore this state don't have to be orthogonal. This is actually the one where I applied the lowering operator. I applied the jump to the ground state, and this state was just weakly changed compared to the initial state. Weakly changed, why? Well, because this excited state amplitude had to give a little bit of the amplitude away to feed into the one photon component. So there's a reduction of this B sitting here. This is why this little blob is a little bit smaller than this little blob you see up there. So that was cool, and of course it does reproduce the master equation. That was our purpose. So we can easily prove that this strategy will actually reproduce density matrices, and that's what interested me at that time. I was doing density matrix simulations of laser cooling, quantizing the motion in 3D. My wave function had 300,000 amplitudes. I didn't want to get matrices that were 300,000 by 300,000, and now I could stay with the 300,000, and then we could actually simulate laser cooling in 3D. So it was a numerical tool, and not much more than that. But I was, of course, also enjoying, also being Danish, that this is actually the Niels Bohr quantum jumps. And Niels Bohr was very, not worried, but he wrote an interesting article in 1928, together with Slater and Kramers, where he commented on the spontaneous emission process. Because he said, now with the quantum mechanics, everything is continuous. There's a Schrödinger equation, it's continuous. There's nothing in quantum mechanical time evolution that is discontinuous. And in his theory, there were jumps. And he still felt that there should be some kind of jump, but he couldn't find out where to put it into the theory. And the Wigner-Weisskopf theory for the density matrix is also continuous. And all the density matrix equations are continuous. Everything is continuous. But here, this is discontinuous, right? So we have actually brought Bohr's quantum jump, exactly Bohr's quantum jump, back into the story. The story is a little bit different than in Bohr's case, because I think in his case, he thought that there was a mechanism in the atom who would make it randomly jump, and then you see the photon. In our case, it's the opposite. It's because we see the photon that the system jumps. But that's, of course, this funny thing with measurements in quantum mechanics, that it's the measurement who triggers the dynamics. And so that is pretty cool. So the quantum jumps are back. The system is driven by the measurement output. So this system is to a high degree driven by the measurement output, by what happens to the quantum state. Truly depends on what you measure. And it doesn't make a difference whether we look or not. Okay? Because if I don't look at the atom, I'm back to the sunglasses situation where I don't see photons. And that means I have to do the statistical average of those two components. And that will evolve continuously. It's not because the system is doing one or the other thing, but it's my knowledge about the system, which in this case is that there was a jump. And in the other case is I don't know if there's a jump. I know there's a probability for having a jump. This situation is related to paradoxes in quantum physics, but it's also as trivial as if you have a light bulb that has a certain lifetime. Of course, it doesn't die after 10 hours. It dies with a probability which has a 10-hour mean lifetime. And if you're in the room, it works and it works and it works, and then it doesn't work anymore. But if you're outside of the room and you ask a person, does the lamp still work? That person would say, well, there's a 60% chance that the lamp still works. A little bit later, he would say, or she would say, there's a 40% chance that the lamp now works. But this probability distribution is correct, right? But it's not the same situation for the guy who looks at the lamp and the guy who's using probability theory to describe that case. So that's really the difference between the stochastic wave function or the quantum trajectory and the average dynamics if you don't do measurements on the system. Here is from our paper. I'm always happy when I see this because, not so much for the paper, because it reminds me of when I was younger. So here you see a two-level atom with a laser on it, and it is doing Rabi oscillations. And in the master equation theory, it does damped Rabi oscillations. That's the solid line solution in here. If you take a single trajectory, there's no damping. It just keeps going up and down, but then from time to time, it is reset in the ground state. That's a quantum jump, and then it starts over again. And that was actually the thing I didn't understand. I was not brought up in quantum optics, so I had not been used to these master equation pictures. And I would think that an atom in a laser field would be oscillating up and down. How could it find rest at 40% excitation when the driving is there and spontaneous emission is taking place? And the answer to some extent is it doesn't. This is what it does in some sense, right? And what you see here is actually not damping of the Rabi oscillation. You see dephasing of the Rabi oscillations. Because if you have many atoms, they get out of lockstep with each other. These jumps happen at random times. And that is why the oscillations are damped in this picture. You may still have a picture in your mind of individual atoms doing full contrast oscillations. If you actually looked at them, that's the kind of story you would tell about them. Now, this is a mathematical thing. You can specify that if you're completely positive, local in time, and linear and continuous master equation evolution, it has to be of this form. Okay, I would also say that this form turns out to be the good description of really many open quantum systems, many dissipative quantum systems. There are corrections if you are non-Markovian, there are very important corrections, but very, very often the master equation can be written of this form where the damping can be described by damping terms, which can be formally written this way. Now, being formally, the equation for that two-level system has only one of these operators C sitting there, which is actually the step-down operator from excited to ground state. But don't look too much at the equation if you're not already familiar with it. But what we can easily prove is that any master equation of this form can be turned into this stochastic approach, where the wave function solves a Schrödinger equation with this H, and each of these C's become jump operators. So we can effectively act with these operators from the master equation to do the stochastic evolution of the system. That means that a lot of smart people in the early 90s already made automatic codes that could turn a master equation into the simulator equation for wave functions, because all the terms can be read out of the well-established damping equation, the terms in the master equation, and tell you how the dynamics could be now simulated by wave functions. So that's cool. That's a universal numerical tool, which we used, and it's still some people using it, but I don't think it's the main application of quantum trajectories at all. That's more in the direction of what our colleagues developed, like Howard Carmichael, who I already mentioned, Howard Weissman, who's going to come and speak here also with Milburn, and a lot of physicists came in with different motivation than us and made formalism, which is the same, but with much broader perspectives. And of course, we are not stupid. We could also see these perspectives. So I have also been working in that direction. So in some sense, the different motivations enforced each other in the way we did this research. I had a very nice dinner with Laios Diossi, who is also here, will speak here, who is also one of the pioneers of these stochastic approaches. And I think we agreed completely that seeing how different researchers had sometimes done this before us. I mean, Laios wrote down stochastic equations long before I did. Was just a pleasure. It was not a disappointment, because you could see that, wow, that was another reason to do that. That was another mathematical insight. So really, really great fun. And I shared just one comment about these different insights, because there were actually different equations for the same system written down. And we were sort of looking at these equations. Why do they get equation which has a completely different form? And that is a funny story related to maybe deeper quantum mechanics. So I already showed you, if I have a two-level atom who decays by spontaneous emission, it emits a photon. If I have a photon detector who says click, then I have this quantum jump I just showed to you. A good question, going back to Einstein's question, where does the photon hit the screen? Why does the measurement random outcome actually appear? You could ask yourself, did the atom jump independent of us looking or not? Okay. It's a difficult question, right? Because if we look, it does jump. And if I don't look, I wouldn't know. But would it be a good theory to assume that the atom is just sitting there jumping? I can definitely in my computer simulate spontaneous decay by this gadget here. But does it also mean that it literally happens if you look away? Okay. And the answer to that question, I can tell you, is no. Okay? And I cannot prove it that it's not the case, but I can tell you an equally appealing story of what could happen in the same situation. So here's the atom again. But instead of putting the photon counter, I can put another device. I can put a beam splitter and a strong field. So I combine this field and this field, so I get half of it going this way and half of it going that way. Half of the strong field going either way, half of the quantum field going either way. So one detector here would see the interfering amplitude of the classical amplitude beta plus the annihilation operator representing this field. The other one would see the minus component. This detector has a high intensity input, which is beta squared or proportional to beta squared. But the important part is the interference term between the two, this guy squared, where you see that you're actually measuring a combination of A dagger and A. And if this beta is real, it's A dagger plus A, so that's the X quadrature of this field. If it's purely imaginary, it's the other quadrature 90 degrees out of phase. But this is what this guy is measuring. It's called homodyne detection. And this is A dagger A. But if beta is a big number, you see, this is irrelevant. That's just a constant. Then this is the quantity you are probing. So you're actually probing the field amplitude of the emitted photon rather than the intensity. Yeah? Beta is this amplitude of this strong field. That's classical, yes. I could also put a B operator representing this field, but then if I assume later on that it is in a coherent state, then that B operator would just extract the number beta, which is the eigenvalue for the coherent state. So this is a strong amplitude, and this is the quantum field, which normally is weak also in the case we are talking about here. So the back action of this measurement would be very different. First of all, there would be really, really many clicks happening, both in this detector and also in the other one, if you look at that one. But if there is a click, then the back action is actually governed by this operator. So you take your state, and then you multiply by a huge number, and then you add what you get by acting with A on it. So that gives you an only infinitesimal change of the actual state. I could also write this as 1 plus A divided by beta acting on the system. So you're really not doing much to the quantum state. So you have really many clicks, but the effect of applying that operator or that operator on the state is infinitesimal in every single case. And what is going to happen is that, well, you are going to add a little bit more amplitude in the ground state, but you will still retain a lot of excited state amplitude. Here you add it with a plus. Here you actually subtract a little bit of amplitude from the ground state. So that superposition is going to have either a little step up or a little bit step down. It's going to diffuse around. And quantum state diffusion was actually the name coined by Jan Percival and working with Lyers, Diossi, and Nicolas Chizin on this work before us. So you have a continuous, in the limit, a continuous stochastic dynamics. Now, Einstein's question, is this what really happens? Okay. Also, if I don't look. So now you can see I have two candidates to what could be really happening if I don't look. And that's one too many, right? I mean, it's not plausible to say that this is definitely happening when I have another model where this could equally definitely be happening if I don't look. So I think we are just in this situation of quantum mechanics that it really matters what you measure. And the quantum state is representing the lesson you learn from what you actually measure. So the jumping or the jittering of the atomic state, they are consequences of the actual and not hypothetical measurements. And of course, in some schools of quantum physics, particularly the Copenhagen interpretation of quantum physics, is almost a dogma that observed the non-measured observables have no value, right? It's only when you measure that you get a value to an observable. It is also only when you measure that you get the dynamics associated to these values. And the dynamics you get depends on what you measure and when you measure. And it is related, so I just cannot refrain from just pointing out the connection to the Einstein-Podolsky-Rosen paradox. So Einstein and Podolsky and Rosen had this paradox of two quantum particles. This is one of the famous pictures of Bohr and Einstein. And when these particles fly apart, then you have quantum states of both. And if you measure the location of one, you would also know the location of the other one. And if you have a picture in your mind that these wave functions are big blobs going in this opposite direction, so this particle, well, over here is in a state which is spread out all over the place, then as soon as you measure this one, then this one collapses into being at the same but opposite position on the other side. So this is the measurement happening here that enforces the collapse of the wave function here. And Einstein didn't like that. Is there a ghost, spooky action at a distance that makes this happen? And he finds there could be an easier solution, namely that these particles were actually already at some locations. And the only thing that happens in the experiment is that you find out where. And when you find out that this one is there, of course, you also find out the other one is here. But the fact it was already there, right? It's not the measurement who drives it. You're just measuring what the hidden variable would have told us. So that is how this big discussion took place. And Einstein says the wave function description does not give a complete description because actually this location was already given before you measured it. But it's not given by the wave function. It's given by something else. And that's the completion of quantum theory that he looked for. And Bohr, this is the 1/3 of a sentence. I skipped the middle part of the sentence, and then I put the last third of the same sentence here. So Bohr says there's no question of mechanical disturbance, and now starts the long sentence. There's essentially the question of an influence on the conditions which define the possible types of predictions we can make. So Bohr says that the quantum state, okay, let me just put that out here. The quantum state is a description of my knowledge about the system. It's not a description of the microscopical state of the system. So when you do a measurement, you change the state because you change your knowledge. Nothing really happens in the physical world, at least not governed by the wave function. What happens to the wave function is something that happens to you because you do the measurement. And then he says, because then that's what he's satisfied with, that these conditions constitute an inherent element of the description of any phenomenon to which the term physical reality can be properly attached. So for Bauer, this is good enough to be physical reality, that my knowledge about what happens in the experiments. Okay, for Einstein, it's not. Einstein, he said, don't you really want to know what's really happening down there? And Bauer, he said always, well, not really, because I already have the wave function description, I already have the probability for the outcomes, and I get the outcomes because I can also do the experiments. So if it doesn't add anything more to make me predict the outcomes of measurements or explain the measurement, then I don't need that physical reality. That's a very non-physicist statement to give in some sense. But there's a direct connection to this measurement stuff, right? Because I'm probing the field at some distance. And B is the emitter, the atom in the story I just told you. And depending on whether I measure the photon number by my counting detector, or I do this field amplitude measurement, there's a different dynamics of this thing going on. So it's really governing on one side what is happening over here. And the true full EPR paradox, as some of you may also know, is that you can not only measure position, you could also measure momentum here, or you could measure position here and momentum there, and get into some potential conflicts with Heisenberg uncertainty relations. And we have exactly the same story down here. And it comes right into our face when we do these theories. So on a formal side, I just want to say a little bit more about measurements, just to tell you also how the formalism is general. I already told you that for any master equation, we actually have a canonical form, and that canonical form immediately translates to this trajectory language. So any non-observed system, if you can do measurements on it, you also get the measurement. But there's a slightly more general description of measurement, which is not directly the master equation, but it is measurement theory. So I just want to show you that on 2 slides. So this is the textbook quantum mechanics measurement. You have an observable, it has eigenstates. You have a quantum state which you can expand. In the basis of these eigenstates, they form a full basis. So this is always possible. The probability to get a particular eigenvalue is just that factor squared, which is the same as the overlap between psi and an squared. And when you have done that many, many times, then on average, of course, you would have gotten an value pn times. So the average value is going to be this weighted mean. And for Neumann, is associated with the postulate that after you have done the measurement, you are into that eigenstate. This is a consistency requirement I'll also come back to, because this is guaranteeing that if you do the same measurement again, you'll get the same outcome with certainty. So this is something you can confirm in the lab, that this is actually happening, and it's very useful, of course, and for many different reasons. This is a postulate, but it's a postulate that we can also validate. Now, we are doing something slightly more general, as I told you, because we are not doing projective measurements on the quantum systems. We are doing another kind of measurements, which are more broadly defined. I'm detecting photons, but I'm manipulating the state of the atom. And it does not go into orthogonal states. So the formalism I just showed to you is not the formalism that describes the measurements. Here is the completely general description of any kind of measurement you can do. So it's called the positive operator valued measure formalism. So that has a long mathematical story to it. But the point is that you have any operator, any measurement you will do will have outcomes, little m. And associated to each outcome, there will be an operator, mm. And the sum of all these dagger m terms is the identity. And the probability to get any particular m is the trace of rho acted upon left and right by this state. If you have a wave function, it's the norm squared of m acting on psi. And the sum, therefore, because of this thing, the sum is going to be 1 of all these probabilities. So this is actually the same as the projection postulate if these m operators are projection operators. Then it's exactly what I showed you before. If you get a particular m, the state is acted upon by m and m dagger from left and right. And that's again the projection postulate. And if it's a wave function, you act only on the left with the projection operator on psi. And that's what I just showed you as for Neumann before. The average, what you can get is, of course, this probability then weighted with the action you do. So the average dynamics is going to be written exactly like this. So rho goes into, if you're unobserved, into a weighted sum of what you get from each of these back actions, and the norm is actually guaranteed here to be normalized or to be preserved. So it is a generalization of the projective measurements, but it includes now the possibility of doing these measurements I just showed you. So if I do the counting, for example, where I can detect a photon or not, it was a projective measurement in the photon space, it's a 0 or 1 photon. In the atom space, it was a jump into the ground state or the no jump, where I'm staying up here. And in fact, there are two M operators here. There's the M0 operator corresponding to no photon. That's the one who translates that state into that state. And there's a jump operator associated with seeing one photon. That's what translates that state into the pure ground state. So these two operators specify the possible outcomes, 0 and 1 detector click, and the whole dynamics is described by that. And of course, they are intimately related to the terms in this generalized Lindblad master equation. The M1 is exactly that jump operator I showed you. And now on the slightly more technical side, but of course I'll not do the full derivation, but if you do the homodyne detection signal, then the current is going to be just fluctuating. There's going to be a mean value of that current, and then you have many clicks in one detector and also many clicks in the other detector. But of course, if you go to the limit of a really strong local field, then you're going to see just tiny fluctuations all the time. And they can be described by a stochastic process, a little Gaussian white noise term sitting here, and your current is going to have this form, mean value plus noise. And the M operator is depending on what is the current that you measure. So there's to each value of this quantity, the possibility that you actually measure precisely that there's a certain measurement back action. And what is that measurement back action? Well, when I showed you on the slide before, I said either you do beta plus step down or you do beta minus step down. And that's also what you do here. So mathematically, and I think I stole this equation from maybe one of Howard Weissman's papers, because he has done a lot in this direction, also the formalism. So what you do on the state depends on the measurement outcome, and this is actually the M operator. You have to do this thing if you measure this particular value of the current to the state. Okay. And look it up, because I don't do the details here, but you can just imagine that the measurement back action can of course be cast also as an operator acting on the state, and this is that operator. And then we are in this general framework of this POVM formalism. The reason that we like that is because we are making a theory of quantum trajectories. We like to make it such that it will always work. We don't want to make it for one particular system and derive that now we can do this trajectory, and then somebody comes to me and gives me another system. He says, I have a 3-level atom. Does it also work for 3-level atom? I have a harmonic oscillator. Does it also work for harmonic oscillator? Yes, it works for any quantum system with a Hamiltonian and where you can measure something, because then this is what we have to do. So all the applications of this technology that many speakers will talk about at this conference is a very, very general form. As general as quantum mechanics itself, we have a Schrödinger equation for every system if we know the Hamiltonian. So that's very nice. And another aspect that I will now turn to is that when you do the continuous measurement, you're not doing this only once. You're of course doing this all the time. So in every time step, you are asking, what is the outcome of my measurement? And if I get the outcome, then I have to do this thing to the state. And then I have to do it again, and then I have to do it again. And every different M I get is going to track me, my quantum state in the space, because I'm going to do all these random actions in the state. And that is really what gives the super good motivation for calling this the quantum trajectory, because your state is doing a trajectory in Hilbert space or in the density matrix space, which is random. Because of the measurement record, it is tracing out this trajectory. So, and coming up to this term again, this thing that happens on average, that was actually explicitly a term sitting in the Lindblad master equation. And the other terms in the master equation can actually be cast into the same form. So the Lindblad master equation on average evolves the same way as these measurements do. So the general proof that it can be simulated by trajectories is also done here at this formal level. So let me just talk a little bit about sequences of measurements also. So if you have an initial state psi, and I want to do the first measurement of anything, and I can get any outcome, and now I get outcome M1. Then I have to act with the operator M1 on the state. I have to do the jump on the state, or I have to do no jump on the state. And the probability for this to occur is the norm of that state. Normally in quantum mechanics, you would then renormalize the state and say my state is the renormalized version, but I'll just keep M1 psi as the state. I can always normalize later if I So this could be the situation, but any measurement could be applied here. Then I do the second measurement. There's an M2, maybe I get another outcome here. So if I get M2, then the state becomes M2 acting on the state. And since the state is M1 psi, I now get M2 acting on M1 acting on psi. The joint probability for getting M1 and M2 in these two events is actually the norm of that state sitting here. If I had renormalized, then I would have to keep track of the probability, and then the probability of getting M2 conditional on M1 would have been given by that formula. But if you take P of M1 times P of M2 conditioned on M1, then you get the joint probability, which is what I write here. So it's the same thing. And you can go on. So if you do n measurements, then you have the trajectory here applying M1, M2, M3, and the index down here refers also to the outcome, of course, that you get all these possible candidate outcomes that you cannot predict in advance, but what is given to you by the experiment, and on a computer we can simulate what we get in these experiments. So that is again the quantum trajectory, and this is the answer then to my little figure before. If I know the measurement record, what is the state? What is given by this formalism? I'm simplifying here. Of course, between the measurements, there may be unitary time evolution. There might be a Hamiltonian too. Then I should put in a little bit of U time evolution here, or I could absorb them in the M's and say M1 represents both time evolution under the Hamiltonian and the measurement back action, time evolution, measurement back action. It would also have such an operator character. But I will, in my lectures, actually the whole week, I will sometimes just draw this one and then appeal to you that fill in the extra dynamics, which is deterministic, together with these terms, and then we will all be safe. So there's this quantum trajectory, and the state in the end is the conditional state. So that is actually the wave function now, or the density matrix now. And now I want to know what can I do with it? And there's actually only one thing we ever do with the quantum wave functions. Well, I mean, you may do whatever you like. You may paint it, put it on your wall. But the thing it can do for us in relation to experiments is it can make the prediction for the probabilities for the outcome of measurements. Right? So the purpose of making a wave function known to me at time t is because then if you want to do a new measurement, I can give you the probability for this. I don't call it M, but I call it omega. That's the interesting operator. What is the probability that the measurement of omega gives outcome number k of that operator? Right? And that, of course, in one sense is just related to the joint probability of all the measurements, M1, M2, M3, Mn up to k. And the way you can translate conditional to joint probabilities is to say, well, this is the probability to get M1, M2, Mn, and k. If you already got these, you just lock them to the values you got, and you only let k vary. And then you get the relative probabilities for getting k conditioned on these ones being true. So if you know the joint probability, that's exactly what we know, then you also know the conditional probability for the last measure. So the conditional probability is varying only k. I write proportional to because it has to be normalized, but all these other guys are the fixed operators corresponding to what you already knew, the measurement you already did. And in fact, you can now, of course, make it more compact. I can call this the conditional state, and then you get the normal application, knowing that state. So a few examples. So this, I'll not go through the formalism with this example. I'll more talk about the physics in this example. So this is my good friend Dieter Meschede in Bonn. He has a cavity system with a single atom sitting inside, a cesium atom, and it has two hyperfine split ground states and an optically excited state up here. And he makes it such that the cavity is not on resonance, but close to resonance with a transition from this state to the optical state here. And the other one is 9 gigahertz away, so far off resonance from that transition. And you have the light going through the cavity. Now, if the cavity was empty, the light would pass through with high transmission coefficient. If the atom is in that state, it is as if the cavity is empty, because you are not resonant with the cavity mode. So if the atom is in that state, the light would pass through with high efficiency. But if the atom is in that state, there's an interaction with the light, and that actually makes the reflection go down, the transmission go down, and some light will be reflected from this cavity. And when he does the experiment, then you get this transmission signal as function of time. So you see low transmission, high transmission, low transmission, high transmission. And Dieter, he came to me and he said, I mean, I know what is happening, of course. The atom is jumping between those two states at these intervals. What is the good way to analyze it? Should I make a threshold line and say if the transmission is above or below that line, then I'm in this state or that state? And I said, of course not. You should think about this as a conditional probability. So you're accumulating every time step a measurement data And that goes back into a statement about the quantum state of this particular system. The probability to be in the ground state might have been very high here. And the fact that it is high, you shouldn't forget in the next time step and look for many photons. You should just say it was high, there's a small probability that it is no longer in that state, but the high detector click confirms that I'm in that state. So that probability will be much better. There are some little spikes here. Of course, they're just statistical fluctuations in the signal. So no matter where you put that line, you will think that it jumped to the other state and immediately returned back again. That's not what is happening here. What is happening here is just a statistical fluctuation in the photon count. So we did that with Dhar. I'm not going to say more about this experiment. This is another famous quantum experiment from Paris, École Normale Supérieure, where Serge Haroche has a quantum object, which is a microwave field, and he interrogates it by sending atoms through this cavity. And this is a very interesting mechanism because the atom is not going to absorb or emit the photon. The atom is going to get a phase shift on one of its two states if there's a photon in the cavity. And if there's no photon, it's not going to get that phase shift. So it's an off-resonant interaction with the field. So when the atom enters in a superposition of one state and another state, it will leave in the same state if there's no photon, but it will leave in a state where there's a minus sign between those two if there was one photon in the cavity. And then they detect whether the atom leaves in the one or the other of those two states. So here's a lot of atoms going through, and every little bar here shows an atom that has been detected. And if it's a red bar going up, it was detected in one state, and if it is a blue going down, it was detected in the other state. And the blue signal here is completely dominant, and that's because there's no photon in the cavity. This is actually the error count, because there's about 15% misidentification here. So you cannot avoid that you get all these clicks. They don't signal that there was a photon in the cavity. They signal the 15% error in this particular experiment. But you can see that there's a completely dominant agreement that there's actually not going to be any a majority vote here would say surely there's no photon in the cavity. And then here for a short while, the other situation dominates, and then it goes back again. And it's a beautiful paper. The title of the paper was Watching the Birth and the Death of a Photon in a Cavity. Because what you see here is a transition between 0 and 1 photon and then back to 0 photon again. Where are they born from? Well, they're born from the fact that there's a low temperature in this apparatus. So there's actually a Boltzmann law who said that there should be 3% chance of having a photon in the cavity. That's the probabilistic description. If you look in the cavity, there should be 0 or 1 or 2 photons in the cavity with probabilities. And when you're looking by this apparatus, you actually find that 3% of the time there will be this red signal dominating because there's a photon in the cavity. So this is how you can turn probabilities into reality, so to speak, right? You turn them into something that you now know. So a beautiful paper. And I'll give many more examples, of course, particular tomorrow, and also a little bit more details on how this reasoning works. A beautiful experiment they did a few years later was that they put not a minus sign on the superposition state, but a small phase shift. So if you only put a small phase shift, you have state 1 plus state 2, or you have state 1 plus state 2 with a phase e to pi over 8, or with 2 photons, 1 plus 2 with e to pi over 8. And these states are not orthogonal, so they cannot be perfectly distinguished. But if you actually measure in a suitable basis, you will find that if there's 0 photon, you'll be 100% transmission in one state. If there's 1 photon, it will be 96%. If there's 2, there'll be 85%. So there's a certain measurement you can do where the outcome probabilities depend on the photon numbers. So that means you have to do many experiments to actually distinguish whether there was 1 or 0 photons in that cavity. But if you do many enough, you can see whether the probability is 100% or 96%. Another way to put it is that every single atom detected here does not tell you what the photon number was, but it gives you a hint. It changes the conditional probability for the photon number because there are different probabilities for those outcomes depending on the photon number. So here's a run with 100 atoms kicked through this apparatus. You start out with a uniform probability distribution from 0 to 7 photons. And then in this particular run, you see they're all equal, and then some get some probability just because of the random measurement record. But eventually the winner was the one with 7 photons in it. If you do the run again, you get 5 or 3 or 2, if you do it many times, because it's the equivalent of measuring a photon number in a state which does not have a definite photon number. So this is effectively a projective measurement in the end, which is beautiful. But what happens towards that final projective measurement is actually the quantum trajectory, which is leading to this state. And here's a beautiful graph where they plot these individual probabilities as function of time, but not for only 100 atoms, but for 10,000 atoms being detected. So in the long run, this 7-photon state will not stay forever because there's loss out of the cavity. So at some point you will lose that photon and another photon and another photon. And what you see here is actually that there's 7-photon amplitude. Well, I think this graph starts with 5. You have 5 photons here, but then the dominant, most likely, is actually the purple curve, which is 4 photons. Then is this turquoise, which is 3 photons. So that at random times, you identify that now the photon number has slowly decreased. If you plot the mean photon number in the cavity, it shows this staircase, and that's the observed system. Of course, if I don't observe the system, there would be an exponential decay law of the photon number in this cavity. But now you have this wonderful story. So this is a really, really great article. And Cedric got the Nobel Prize in Physics 2012. There was, of course, a direct reference to this kind of work and this particular article, because he's really monitoring the quantum dynamics of a system at this microscopic scale. He's watching the real dynamics of the system. Of course, in tandem with affecting it himself by doing the measurements on it. Now, the rest of this talk, I'll talk about a question I asked myself in the early days of this trajectory business, but it took 20 years before I had a good way to answer it. And I like to share it with you because it's also now one of the tools, at least in my toolbox, for what I'm doing. At Howard Weizmann has also fantastic research going in this direction. A slightly different appeal than what I do. So I already talked to you about this motivation. If I have a signal, then I know what is the state. Okay. In this figure, there's also the signal coming later. And of course, at any moment in time, I can use the entire signal to infer what is then the state here and here and here. But I was wondering, what does this signal actually tell me about the system at the earlier time? Okay. So if you are living in the classical world, sometimes discoveries we make now inform us about the past. I mean, that's what archaeology is about. So archaeologists, they don't change what happened 2,000 years ago, but they do discoveries that make us rewrite the history book. And if you have a system which is very excited, later measurements of a lot of photons will only confirm that you were very excited. But if it was less excited, later detection should have fewer photons in it, right? So you should learn something about the state of the system at that moment in time, also by the later measurements. Okay. So I think I probably asked myself this question in 1993, and then I figured, what am I going to do then? Am I going to use these measurements and act on this row to get a better row out of it, right? And I just couldn't find any formalism that made sense. And then, of course, you go and do other things in science, and then you come back to it again later. And maybe I'd advise to the young people in the room, if you have something you can't solve, but you find interesting, it's not stupid. Write it down, because later you can go back to it. And I've actually, I think 3 or 4 of the things I'm most happy having done, maybe not what other people are happy having seen me done, but things I'm happy having done were things I thought about a long time ago when I was young and smarter than now, but not smart enough to solve it. And later I become smart enough to solve it. So now I'm out of ideas, but I have more techniques, right? So write down your questions. No question is a bad question. Maybe later you'll find out, yes, it was a bad question, but there was still something in it that could turn into a good question. Maybe you could also only do that later. So I had this question, and it was bugging me, and then of course I couldn't really do much about it. There must be an answer to the question, though, because there must be information in this record that also tells us about the system in the earlier time. I found out that it's not what is the right answer, it's actually to ask the right question, and then answer the question after that. And I'm very inspired by the Copenhagen interpretation, so I'll offer you that way, and that's actually how we came to it. Because the right question that we have here is, what am I going to use that knowledge to do? Right? Because if I'm too much stuck with the formalism and it wants to be a row, that's maybe not what I need. What I actually want is knowledge that has to do with what quantum mechanics tells us. And what is that? That is, if somebody was to do a measurement here, I could use this row to tell the probabilities for the outcomes of that measurement. The measurements I do later, can they give me better, more precise values of those probabilities? So the question that, at least the question I found meaningful to ask is, what do these later measurements tell me about the probability that somebody got outcome K of a measurement that he was doing there? And then I made that theory, and that was not difficult to make. Okay. So that's the theory, and I will derive it tomorrow. I just tell you the result now. So I already have these many measurements, M1, M2, up to MT minus 1. This is the exciting moment time, which is what we're going to look at. But time continues. If I do these measurements, there's a POVM I can do at this time t, omega k. The probability of getting the kth outcome is what I wrote on the previous slide. This is given by this formula, trace omega rho omega dagger. Now I keep doing measurements on like this and this and this and this. And this is now. And this is where the moment where I want to go back and revisit what was actually the probability to get these outcomes, conditioned on me knowing everything before and everything after. And that is the normal situation in the lab, also in our Roche's experiments, because he has done all these measurements. And now we can ask, what is the probability that there are photons in the cavity at that moment in time? That's the graph he showed, but he only used the earlier data. Now I'm going to use also the later atomic data to see, do I know better what was the photon number in his cavity at that moment in time? Or to phrase it more precisely, what is the probability that he would get n if he measured n at that moment in time? Because that's the real meaning of the probabilities in quantum mechanics. So the good question, what is the probability for having obtained that outcome? We could make a betting game, right? You measure and you don't tell me what you get. And then I keep measuring here, and then we're going to make a betting game. Can I guess your outcome? Or we can make odds, so we can put in money. And then, of course, it's very important I know the odds. So I have to know the probabilities as well as possible before I'm going to gamble with you in a casino like that. And there is a new formula. There's actually a matrix object. It's called the effect matrix. It already existed in the measurement literature. And it is compiling the effect of all these measurements. Technically, it's calculated as a matrix that evolves backwards in time, incorporating the effect of all the M operators, the measurement operators, having to do with this sequence. But I'll show you that tomorrow, so I'll not hang in the formalism now. But there's two matrices who provide the probability. There's the rho matrix, as always, containing the prior knowledge, and this E matrix taking care of the posterior information you get, and the probability is sandwiched in this funny way to get the result. So this is the newborn rule if you have also later data to support your guess. And I call that pair of matrices the quantum state, because for me the quantum state is not psi or rho. For me the quantum state is the mathematical object who gives me probabilities. And it gives me any probability because omega doesn't have to be specified. This is for any measurement you would do, right? So it's the same as the wave function who can tell you position outcome, momentum outcome, energy outcome, angular momentum outcome. It's all in the same quantum state. You just have to put the right operator. We just have to put the right operator, and then this pair of matrices will do. And because things don't commute, I cannot just multiply them and say this rho times E, because this omega may not commute with them. So this formula actually has to stay apart. So the quantum state contains these two inputs to our description, and this formula is actually an easy formula to use and evaluate. Einstein would have maybe been unhappy because that means that this state at the past would be affected by later measurements. So this is spooky action in the past. And Bauer would have replied, well, it's not an influence on the system, actually. It's an influence on the conditions that define the possible types of predictions regarding the past behavior of the system. I get wiser with time. I don't change the past. Archaeologists also don't change the past. They get wiser about the past. So this is, of course, the nature of quantum physics. We made the formalism. And then I talked to Serge at a conference and asked, do you still have the atomic data? Because I would love to just run your atomic data that led to this figure into the formalism. And I'm still actually feeling something in my throat. I'm a sentimental person about science sometimes, because I was completely shocked when I saw what we got. So this is actually what we got. So this is not me cheating and removing all the noise in the upper graph. This is just what the data says. The probability of having 3, 4, 5 photons at that moment of time is 100% or 0%. And the transitions are clear. Of course, you are in doubt in the transition phases because, but there is the transitions. So this is really what we get. And why is it like that? Well, let's of course take a point here. All the data points up to that point are in agreement with the photon number being 1. So there's a probability, because there are still some fluctuations. Sometimes you don't hit 96%, but 98, or sometimes 94% if you look in small intervals. But the larger interval is averaging nicely out. But there are fluctuations here. The future measurement confirmed the same thing. So your error is actually squared. The probability that you are not in that state is now multiplication of those two events. So if it's 5%, it becomes 0 to 5%. And that is what we see down here. Right? There's a huge reduction. And all the spikes are gone, because this spike is not because the atom is on the way of transitioning into the other state. That spike is just the counting statistics, that you in that interval should have had, I don't know, 42 out of 50 possible clicks in your atoms, and you got 48. Okay, but of course every single counting is a random event. So of course you will sometimes get 48 instead of 42. It's not likely, these spikes are rare, but every time they happen, of course they're sitting there. But if the next measurements go back and show the probability corresponding to the 96%, then of course you realize that was just a spike, a statistical fluctuation. So the spikes are just completely gone. This is also why in classical signal processing, this is called smoothing. It's not smoothing cheating with a pen. It's the theory that smooths the result. The results become smooth when you use the full theory. And Weissman has done some of this work, and he calls the procedure he does quantum smoothing. And once I also called what I did quantum smoothing, he said, that's not the same thing as I do, and it's right. So I apologize to Howard for having used the word quantum smoothing. I will go back and use this past quantum state reasoning for exactly what I do here. But the effect is, of course, the good one. And this is not a big disagreement between me and Howard. This is just showing that we can have different purposes. But we have a smoothing effect, and we have what I would call much more certainty, much better understanding what is going on. In the paper with Serge, we actually could now measure the length of these intervals and estimate the decay rates much more precisely than if you look at this guy and try to estimate what is the decay rate. So we could even do some kind of tomography on the functioning of the system better, having this record. So if you ask, what's the use of retrodicting the past? It's already past. I mean, so a part of our historical interest in what was the field state a millisecond ago, what is the use of it? But we actually learn other properties of the system better from better measurement records. So that is nice. We had a nice and interesting comment from a referee, because the referee said, cool guys, but what you're really doing is you're showing what you think is the probability of being in that state, because we are inferring the probability of the photon number in the cavity. But is this curve right? When I say that it's 100%, is there actually the photon in the cavity at that moment in time? And we don't count the photon, we only count all these atoms. So we have actually not validated that it's true what we say. And that's true for all quantum trajectories you will hear about at this conference, that we infer the state of the system. But that state of the system is only confirmed by the same record as the one who creates the state of the system. So the referee was saying, this is not good enough. And I was actually laughing a bit, because this paper also didn't prove that this graph was right. And this was published in Nature. And Roche got the Nobel Prize in physics. And then we come 3 years later to Physical Review A, and we say, look, we have a better analysis of the same data. And then the referee is complaining. But of course the referee was right. Okay, so it's an important point. So what we did was, we said, let's have the cavity predominantly empty. And then we asked secretly a guy in the room, please inject a photon. That means send in a resonant atom who will certainly put a photon in the cavity at one point here. And don't tell the other guys. And then let's see if we can infer when that happened. And that is shown down here. It was atom number 4000 who put a photon in the cavity. So the red curve is the normal density matrix result. What is shown here is not population, it's the mean photon number. But when it goes from 0 to 1, it's because you realize that there's a photon in the cavity. And you can see that if you read the data in time, fluctuations, of course, as always, and then after 4000, after few atoms have been detected, you start realizing something has happened. The statistics has changed. But of course, you have to detect a few hundred atoms before you can distinguish 100% and 96%. So therefore, you need some hundred atoms. And there's a lot of noise in this curve. But it's there, it's late, and it's noisy. Okay? The green curve is our theory, okay, on the same data. So it actually says, spot on, you jump very fast up here. And if you ask, when is it 50%, where's the switch made? It's actually at atom number 4000 in this simulation. And the reason is, of course, that I know all these later statistics when I produce the green curve. So the fact that there's this change happening here is known to me because I'm analyzing the data on both sides of that. Here the photon leaves again. Nobody knows when it leaves again, right? Because that's not known to us, but the statistics infers that it leaves again. And the normal density matrix says that it happened here, but that's because the normal analysis, of course, has to realize that the photon statistics has changed, and it actually comes with a little delay. So again, you can see that if I use the data in both directions, the green curve actually comes down a little bit earlier than the red one, because that one knows that the future data are already in agreement with zero photon in the cavity. So that was the proof that this is also probabilities that actually reflect reality in the lab. Now, I heard a bell ring, and I did not even, I should have said in the beginning, you should ask questions all the time, because then we don't need question time at the end so much. But of course, I just apologize for speaking for so long. I think I'll skip not important slides. Maybe it's not even, but I'll give more examples, of course, exactly on this physics tomorrow. I have some very nice little story, but I miscalculated the time a little bit. So I think I just go to, can I just do that like this? Yes, I want to maybe take the one before that. So the summary and what I've been talking about today and what I'll build on tomorrow is that we have, of course, these ichthyosaurs. That's a motivation of the physics of individual systems, which I guess you all agree with. The dynamics of these systems are affected by measurements, also if they happen from a distance, and even if they happen from the future, if you allow this past quantum state to actually be a quantum state. It's not a paradox within a Copenhagen interpretation, because quantum states are what I know about the system. It's not something that happens literally because I do something. And then these states are just mathematical objects that quantify our knowledge. And they are working like that. They can be used and they can be tested because it's knowledge about experiments, and you can do those experiments and we can compare. What happens in the reality in the microscopic world is not answered by quantum trajectories. What Einstein's question is not answered. There might be an answer to that question. Bohr does not say there's not an answer to that question. He just says he doesn't want it, but it could definitely be there. So the more philosophical side of it is that we should still keep pursuing other alternative ways to understand quantum physics, going even further beyond being able to predict outcomes of measurements. But standard quantum mechanics is in a good and healthy situation with this theory. But let me finally have a quote here with Niels Bohr about quantum mechanics just a week before he died. If we should one day wake up and realize it was all just a dream, we would still have learned something. And they said that about quantum mechanics, and I say that at every talk about whatever I talked about. So we would still have learned something, even if it was wrong, everything I told you. Thank you for your attention.
Question?
I see Sai has a question over there.
Yeah, I jump in. My name's Cedric from Washington University. I'm thinking about this nice experiment from Michel several years ago to catch and reverse a quantum jump mid-flight, where they have a bright state and a dark state, and they're monitoring fluorescence. And at some point, the fluorescence goes away, and they eventually infer there's a quantum jump to the dark state. And in that, there's some very coherent quantum dynamics. The atom makes a completely coherent thing that they can reverse with feedback. Yeah. How does that play with the quantum state, the past quantum state story? Could you have made a better feedback, or does the quantum evolution, due to the absence of detector clicks, change in hindsight?
Thank you. That's a very good question. Of course, I already mentioned myself that what is the use of knowing something too late? Because the feedback, you would have liked to have done that at that moment in time. So you cannot go back in time and do a feedback. But you can, of course, maybe you can say you can estimate better what was the state, and if there's a state who has a trend in going somewhere, then you might actually benefit from having that trend, because that can reinforce also your knowledge about the state now in some way, right? I've not seen people doing it on the quantum state itself, but I've seen people doing it on looking for drift in parameters in quantum systems like quantum computers. So you are using the inference and this past mechanism to get better estimates of a slope in a parameter. And I could imagine you could imagine something similar with the quantum state. Of course, that experiment, I mean, just to comment on that experiment and Howard Carmichael was, if you're not co-author, then at least he was the idea person behind that experiment. When we do the homodyne detection, the state is pure. And also when I do the counting, I have pure quantum states, unless there are many other dissipation channels. So if you monitor decay, it is not an incoherent process. In fact, decay is never an incoherent process. But in the bigger Hilbert space, it's unitary. If you trace over the field going away, you have lost that information. But if you measure it, you have retained information, and you have repurified the state. So if you measure at atomic decay by homodyne detection, you have a superposition state, and you know where it is. And that means you can, of course, invert it, because you can just rotate it back again at any time. And there are experiments at Berkeley where they were maintaining a qubit alive forever. And of course, you do it because you prepare the superposition state, and depending on your measurement record, you kick it a little bit up and down to keep it in that position. You're not violating any laws of quantum mechanics. You actually reinstall it in a state you already know. You could also just have let it die and prepare it later, but they could also do that. They could also see Rabi oscillations forever. And what they did was they monitored the decay from the system by homodyne detection, and then it's going a little bit too fast, a little bit too slow, but then you just give it a little extra notch, and then it will follow the perfect oscillations here. So there's actually a number of things we can do without past quantum state, of course, but just the in-time trajectory. I guess what, I'm not good at, okay, short answer, thank you.
Hi, so thank you for this talk, Klaus. So my question is basically, if I have data from, let's say, 0 to t, there's only that much information there. And so if I tried to do, let's say, I wanted to do state estimation, or I wanted to know what the quantum state is, or some parameter estimation, then in a Bayesian sense, I could basically put down a prior and then try and evolve it down. And to me, what is surprising is the fact that so what I want to know is, this is a doubt I have about smoothing per se, and also which is that when you do this backward propagation, somehow it feels to me like you're reducing the error bar at that time in the intermediate time, T1, between 0 and T. Yes. But to me, it also feels like there's only that much information in the system. So whether I forward evolved it to the end time, or whether I backward evolved it, there's only that much information, right? Yes. So I could predict, to me it feels like I could predict with more certainty something in the past, or I could predict with more certainty something here, but I shouldn't be able to do both. And am I wrong, or is this?
No, you're not wrong. So, and I think I'll show you a figure in my Thursday lecture where I come to sensing in particular, right? And it's actually true, if you do sensing for a long interval in time, you will have a long period in the middle where it's completely flat, the ability to sense, because either you have the information from the past or you have it from the future, but it adds up to the same amount of information. Of course, the quantity can still be fluctuating, but your ability to follow that is the same throughout. But then in both ends of the interval, the error actually increases. And that's, of course, because in the beginning, you need those earlier points that you don't get anymore. And the same in the end, you need the later points you don't get. And the quantum systems will typically have a finite time over which it forgets everything, right? There's a damping time in the system. So when I'm saying I'm looking backwards in time, I'm looking at all 10,000 atoms. Any moment in time, it will be the nearby 500 to 1,000 atoms who really matter. Much later measurements have very little to do with the state at that very early time. And the same with the sensor. Much later measurements have very little to do with the perturbation at that time. But I'll show you, and I'll also maybe show that's a little bit out of that context, but we also tried to apply machine learning to such a thing. So we just give it the data, and we knew what we had trained it on, so we could train the network, and the network did exactly the same. So of course, I don't know how the network thinks. It has 4,000 free parameters to fit everything, but it actually suffered, of course, from the same lack of good information at the edges.
Yes, Tristan Benoit from Toulouse. I was just wondering if you tried to, instead of conditioning on the full past and a full future, have a window of time like before and after, and see how it depends on the size of the window, this smoothing.
Yes, that's a lovely idea. I mean, I haven't done it myself, but it's exactly as you say. What you still have to put something we could call the prior at the edges of that window. And maybe you would then say, if I have not measured anything up onto the left side of that window, or that's from this side where you're sitting, then that would maybe be the steady state density matrix, if it's a system who has a steady state. And coming from the other side, I would actually put the identity for this E-beast, because there has been no other things happening on it. And then I would only include the right-hand side. Great idea. I mean, that could be fun. And I believe that such analysis has been done, maybe actually by Pierre Rouchon and Benjamin Huard, in some of their work where they played a little bit with such windows. But, I mean, and depending on the dynamics of the system, you will see many things. There's actually also in the trajectories, what is the dynamics of the system? It can be, there's a damping rate from the master equation. It's not a scalar because they are different, it's a matrix equation. But there's damping going on and there's oscillations going on. And you get information from both, of course. So there's also a difference whether you have only damping or you have a system which is very oscillatory at the same time. So the window size is not a trivial function of the damping rate as I see it.
Pierre Guillemin from Paris. Thank you very much for the lecture. So you've showed how we can simulate the evolution of an open system by averaging over pure states which have jump, but you also explained that there is another picture, which is that you can evolve pure state with diffusive measurement. My question is numerically, so you have two options to simulate an open quantum system, which is a jump or diffusive unraveling. Are there situations in which one will converge better, so the error will be smaller in the number of trajectories?
Yes, that's a wonderful question. And we thought a lot about it because we had these production runs for laser cooling, right? So I really wanted to do it the best way. And of course, you can imagine that if I have a variable and I want to know the distribution of it or the mean value of it, then the different wave functions could be brought. And then they would come out with candidate values for the mean value of the operator. So this would be mean value of A in run number 1, mean value of A in run number 2, and in run number 3. And then, of course, you would have to take their average to get the mean value of A, which should be equal to the density matrix mean value. If you had a situation where your simulation led to more compact wave functions, then they would be more narrow. But that actually means that since the average also of the precision distribution should be the same, these guys would have to scatter more than these guys do. It's a little bit the same. So here's a hill, and over the hill, there's a road, and there's you want to know where is the road, but you only see, sorry, I don't want to show you the road yet. You see a cyclist. And you ask, where is the road? But I can't see the road. And of course, the road could be from here to here, or it could be from here to here. Sorry, from here to here, or from here to here. Right? Because he's on the road, but he could be the left side or the right side of the road. Of course, if it was a truck, it would be a little bit easier to guess where is the road. So using fat wave functions gives you a better sampling of mean values, because fewer of them will actually do the mean value in a good way. Unless the cost of running these wave functions is calculated into the thing, because if your wave functions are more tight, you can use a confined Hilbert space to lower dimensions to keep track, and then you can have a kind of running basis for your individual wave function. So there's a lot of items going into this thing, but certainly there's a difference, and it's exactly here that the choice of measurement you do is making a difference. The quantum jumps gives population statistics that fluctuate more, while the homodyne detection is more equilibrating the populations.
Thank you.
Hello, I'm Ingita from Griffith University. So my question is, in case of the retrodiction, if I have a jump, if I'm looking at a quantum jump trajectory, and if I look at a trajectory which does not have any jumps, then will the retrodiction give more information, like will it be a better estimation, or it will capture only the effects when there is a jump in the trajectory?
Nope. It will also capture the effect when there's no jump. But the no jump is also a POVM M operator, M0, which also changes the state. I didn't tell you the detail how it changes the state, but if there's no jump, there was a loss of the excited state amplitude just because of the possibility of transferring norm to the single photon. Right? So the two-level atom has a population in the excited state, but some of that goes into the ground state when there's a photon leaving. So the no-jump dynamics is accompanied by a reduction in that population. It's actually accompanied by dynamics, which is like a non-Hermitian Hamiltonian, which is H minus I over 2 C dagger C, if this is one of my jump operators. So you have a non-Hermitian Hamiltonian, and you have to apply that. And this is causing an extra element of dynamics, also to the E. And if you have been looking, and so this is actually, this is funny. I can talk about this for hours. Do you have the time for that? When is the next talk? No. If you have an atom in a superposition state and you see no click forever, the atom will be in the ground state with certainty. Right? It sounds like a Bayes rule argument, right? Because if you don't see clicks, it's more likely that it's in the ground state. But it's also what this dynamics does, because you have this effective decay rate here. So there is a lesson learned from no jumps. And if you, if you, maybe I should be a little bit careful. The final state, since it's completely unknown, is a little bit like it could be equal probability of those two. But if you have a long record with no clicks going backwards in time, you will actually gradually increase the population in that state up here. The jumps does something similar. Just before a jump, the atom is in the excited state in retrodiction. Why? It could not have been in the ground state, because if it were a ground state, there couldn't be a jump. Right? The atom cannot emit a photon when it's in the ground state. So the projective measurement before a jump has to stay excited, because the probability that it says ground is 0. So the jump tend to go upwards, and the same, this no jump decay also goes upwards.
Last question.
Great. Thank you for the nice lecture. So Gonzalo Manzano from Mallorca. So I was wondering if this retrodiction can be thought as a kind of post-selection on the.
Yeah. It's so there's a lot of beautiful works on post-selection prior to this, associated also with Yaki Aharonov and others, and he has also made famous paradoxes and interesting things. Everything I talked about is in complete agreement with that. You can say I have a slightly broader, I can do something which is not part of that theory, because I'm doing the full dynamics, right? So I'm not post-selecting on a specific event, I'm post-selecting on what actually happened. So there's no selection. This works for any experiment, because I'm not interested in looking at particular special cases. I'm interested in saying, what do I know now? So that's the slight difference between this and the Aharonov school, where you say, look, if I got this and if I started with that, then the middle would be very interesting. Right? I think it's always interesting, but obviously the extreme cases by Aharonov are ingenious, because they are not only interesting, they're very interesting, so very exotic. But there's this connection, and I'll also make that a little bit more clear tomorrow.